Hello and welcome back. So I've done some thinking about how I presented the last part of question 3. And that's where I said if 1 radian corresponds to a 1 unit change in time, then if I'm going to double the speed, if I'm doubling the speed that the ball is rotating, that means that we are going to have to take an input t and double it because we're going to be traveling half as fast. And this still kind of works with how I explained the last part of question 3, right? For a 2 change in theta, we would need a 2 change in time. And so that's why we get this result. If we're going to, instead of completing a full revolution in 2 pi seconds, now we're going to do it twice as fast, so we would complete a full revolution in pi seconds. But if we're speeding up, certainly we have to, if we're becoming twice as fast, certainly we have to, when we're inputting our values for t, we have to double them. Okay, so let's try and make more sense of this using this table, right? So when we travel theta radians per unit time, or when we travel 1 radian per second t, the amount of time to travel pi over 4 radians, of course, is going to be pi over 4 seconds. And for pi over 2 radians, that's going to require pi over 2 seconds. And pi seconds for pi radians, and 2 pi seconds for 2 pi radians. Now, if we were to consider the same values of time, pi over 4, well, since we're going to be traveling twice as fast in pi over 4 seconds, now the value of theta is going to be twice as large. So 2 times pi over 4 would be pi over 2. And for pi over 2 seconds, we would have traveled twice what we traveled here. That would be not pi over 2, but a whole pi, and so forth. For pi, we'd have 2 pi. And so if we wanted to establish what is driving theta here, we would just take our units of time from our 1 radian per second scenario, and in each case, what do we do? What are we doing with theta? We're doubling it, right? So pi over 2, or I'm sorry, 2 times pi over 4, 2 times pi over 4, of course, is pi over 2. 2 times pi over 2 is pi, and so forth. So hopefully that drives home the point that theta now, the argument, the input to our functions are going to be replaced with 2t and not t. Okay, so now that we have the somewhat, well, I guess, difficult to explain nature of what happens to our argument to our function, we can say that since we're driving vertical distance, our function is going to be the sine not of t, but of twice t, and we're going to adapt our units, our radius lengths, from 1 radius length to 2.3, which is why we get this result here. So in part C, when the ball was swept out from the 3 o'clock position, a complete revolution around its circular path that took for theta equals t, that took that would be a 2 pi radian change. We said 2 pi took 2 pi seconds. So now we are going to complete a complete revolution. We're going to complete 2 pi in half the time. So instead of 2 pi seconds, we are going to complete 2 pi in pi seconds, half the time. Okay, so I guess we'll go back to the tables to look at number 5. It says now, instead of traveling a whole radian per 1 second, we're going to travel half of a radian per 1 second. So that means I've listed our values for t and theta when our speed is 1 radian per second. Now, if we traveled pi over 4, if we swept out pi over 4 radians of openness and pi over 4 seconds, now we're going to sweep out half that value of theta. So that would be pi over 4 divided by 2, which is pi over 8. And now in pi over 2 seconds, we are going to travel half the distance we did in this scenario. So that's pi over 2 divided by 2, which is pi over 4, and so forth. For pi seconds, we're going to travel not a whole pi, half that distance, pi over 2. So in general, we just multiply our argument time by 1/2. So another way we can write this is 1/2 time, or t over 2. Okay, and so now since we're still relating vertical distance, we'll use the sign, and since we know our argument has to be t. We have to multiply our input time by half to have it, because we're going to now traverse an arc subtended by an angle in radians that is half per unit time, right? So we have our argument as 1/2 t, and then of course we adapt our units for radius length 2.3. And they want us to call this function j of t. So for part C, let's again compare to when our units are proportional, as in 1-to-1, 1 radian per 1 second, to traverse an arc subtending from 0 to 2 pi. You know that took 2 pi seconds. So now in the case of where our argument is 1/2 t, to travel from 0, 1 revolution, 2 pi radians, that's a complete revolution of the circle. Since we're traveling at half the speed, that means it's going to take us twice the amount of time to complete a full revolution. Okay, so then when our argument is 1 radian per 1 second, we're just going to have our standard sine graph, right, where we have a longer radius. Our radius is 2.3. Now, for subsequent questions, for example, if we looked at for 2.3 sine of 2t, double the speed, well, that tells us that we're going to complete a full revolution of the circle at pi radians. So we'll have a picture that looks like this, right? We complete a full revolution in half the time. And if I were to look at, why don't we just move forward to the next part of this question? Okay, yeah, so that's what in part B, if we were to overlay our standard sine graph, which completes a full revolution in 2 pi, and that would be 2 pi radians. And now h of t was 2.3 sine 2t. Of course, we're going to complete a full revolution in pi radians. So our graph will look as follows. Now, for j of t, which was 2.3 sine of 1/2 t, it's going to take us, if this is, we'll say that's pi, this would be, let make that pi over 2. This is pi. This is 3 pi over 2. This would be our 2 pi and so forth. So now, since it's going to take us twice the amount of time to complete a period, meaning we're traveling at half the speed, so that tells us that after 2 pi, we will only have completed, of course, let me just draw our standard curve here, from 2.3 to negative 2.3. Let's draw our standard sine graph where we complete 2 pi in 2 pi seconds. Now, after 2 pi, we won't have completed a full revolution, but rather a half of a revolution. So we'll have a picture like so. And just to make that clearer, for amplitude 2.3 and negative 2.3, we would complete, our standard graph would look like so. Right? And now for j of t equals 2.3 sine of t over 2, we would have a complete revolution in 4 pi. So we'll have this graph. Just kind of enhancing what we established previously. And again, so the reason here is if we're traveling, the reason we want to use for all of these is the thinking that if we're going to travel twice as fast, that means we're going to cover, as in 2t, we're going to travel twice the speed we're traveling twice the speed, so that means we're going to cover double the amount of angle measure in the same amount of time. And as we saw in part C, if we're traveling at half the speed, that means it's going to take us double the amount of time to traverse an arc subtended by an arc of the same length. We'll pick this up in the next video, but I thought I'd highlight the importance of understanding what a period is, and the period is, of course, the interval of input needed to complete a complete revolution of the circle. See you in the next video.